Hi, and welcome to the integration presentation by the connectivity section. This presentation will go over the work we did on integration in semester 1 of 2020. So in terms of the motivation for this project, at the end of 2019, MCAV successfully demonstrated live vehicle tracking using a Cohda wireless onboard unit and a roadside unit. So the onboard unit was situated inside the vehicle and the roadside unit was set up next to the road. This was achieved using vehicle-to-infrastructure connectivity. The logical next step for MCAV was full integration of the OBU with the Nvidia PX2. The Nvidia PX2 is the central brain of the car. This would enable the OBU to interface with ROS, Robot Operating System, or the software that controls everything to do with the car's inputs and outputs. Integration of the OBU and interfacing with ROS allows the transfer of useful data between vehicles in V2V applications. It also expands the possibilities of V2I projects. In terms of the requirements, we needed to create a device driver to send and receive data between the onboard unit and the Nvidia PX2. It needed to be able to access ROS messages and transform it into a data format that works with the OBU that can be sent over the wireless connection. We are limited by the connection type between the OBU and the PX2. And another limitation was that we couldn't install ROS onto the OBU. So complex messages, such as ROS messages, are not supported. They needed to be represented as a string. We also need to consider the DSRC bandwidth limitations. How much data can we actually send in a given amount of time, and what data is the most important to send using the wireless connection? On the PX2 side, the connectivity team has developed an OBU device driver written in C++ that receives data from ROS and serializes the message for transmission. There is a client-server relationship set up between the PX2 and OBU to enable two-way communication. This is facilitated through the boost.asio library.
So, to reach the next goal, it was necessary to establish radio control between the units. To achieve this, various methods and example scripts were run. A basic TX and RX script was run to test the target rate, current rate, and package transfer. One unit was established as the server unit to send packages to the client unit. Over this 802.11p radio module, the logical link controller LLC commands could be used to send IPv6 data without using the example ETSI or example 1609. After this, custom Python scripts were used to send UDP packets to the TextTX app for connection assurance. As the connection between the RSU and the OBU had been tested previously in 2019, scripts such as this example 1609 were customized to send custom messages to the OBU from the RSU.
Here's a final look at the integration architecture from the integration project by Connectivity in 2020. So we have the PX2 with ROS running with a TX driver program, which sends serialized data over the Ethernet connection to the OBU. The OBU then runs some proprietary applications written by Cohda Wireless and customized by the connectivity team, and this information is sent over the wireless connection. When the OBU receives a new message from another OBU or RSU over the wireless connection, it's then forwarded using the same Ethernet connection, and this data is collected by the RX driver, which passes the serialized data that's been received and hands it back to ROS in a supported message type.